Hi there, welcome to this Elkchemist chemistry practical video looking at rusting and the factors that affect the speed of rusting. So rusting is a form of corrosion unique to iron, and effectively what rust actually is a compound known as hydrated iron 3 oxide. And it's not great for the iron because it is weak, brittle, flaky, and it compromises the structural integrity of the iron metal itself. So we want to try and avoid rusting as much as possible. So what I'm going to do is multiple different environmental experiments with little iron nails. I'm going to take you through each of these test tubes and the environment we've created around the nail, and in about a week's time we're going to come back and look at the extent of rusting in each of these mini experiments. So experiment 1 is just a control experiment with an ordinary iron nail in some cold water open to the air. Experiment 2 may look identical, but actually I've dissolved a pinch of salt into the cold water to simulate seawater or salt water and the effect it would have on the rate of rusting. Experiment 3 contains freshly boiled water around our iron nail. And I've also sealed this boiling tube with a bung to prevent any air getting in after I sealed this boiling tube. Experiment 4 contains no water. And actually, this white solid at the base of this open boiling tube is known as anhydrous calcium chloride. It's a white solid and it's actively absorbing moisture from the air. It's a drying agent. So this is a very dry environment around this iron nail. Now in experiment 5, the actual nail looks a bit blurry. Do not adjust your set, that's actually on purpose. I've coated this iron nail in petroleum jelly, which is a thick, viscous, oily layer completely surrounding and encoding that iron nail. We're going to see if that makes a difference to the rate of rusting. Now in experiment 6, I have wrapped a piece of this metal, magnesium, around the iron nail. So this iron nail is constantly in contact with this piece of magnesium metal. We're going to see what effect that has on the rate of rusting of the iron nail beneath the magnesium. Now in experiment 7, I've used this metal, zinc, instead of magnesium. I've wrapped this metal around my iron nail. And in fact, I haven't even bothered to completely cover the iron nail with my zinc wrapping. We're going to see if that has an effect on the rate of rusting. And finally, in experiment 8, we've wrapped our iron nail in a different metal. This time we've used beautiful copper as our wrapping in contact with the iron nail. We're going to see if that has an effect on the rate of rusting of the iron nail beneath. So, just before we leave this experiment for a week to do its thing, you might want to grab a pencil and pen and write down some predictions of the extent of rusting you expect to see in each of these mini boiling tube experiments when we come back after that week of time. And then when we reveal the results, you can see how close you got to the reality of the extent and rate of rusting in each of these micro experimental situations.
1 week later.
So we're back after 1 week. We're going to look at the extent of rusting in each of those rusting experiments. Experiment 1 was our control experiment. We had an iron nail with access to both water and oxygen, and you can definitely see some rusting has occurred there. And that's really important for our understanding. For rusting to occur, iron must be in direct contact with both water and oxygen. Now, experiment 2 had a little pinch of salt in the water. And it appears to be the case there is more rusting around the nail with the salt water than there was with the ordinary water. So it appears to be the case that salt increases the speed at which rusting occurs. Now, I wouldn't say that salt is a catalyst for rusting, but it certainly seems to be an advantageous environmental factor in increasing the speed and extent of rusting over a short period of time. Experiment 3 is interesting. Now this was the experiment where we had boiling water around the iron nail, and we also sealed the experiment with a bung to stop any fresh air getting in. And the extent of rusting is much, much lower than the first 2 experiments. It's a bit around the ends of the nail, but compared to the salt water and the normal temperature water, we have much less rusting going on. So why would using boiling water massively reduce the rate of rusting over that period of time? Well, the key idea here is that at higher temperatures, dissolved gases have a lower solubility within the water. So at the high temperature, there will be a lower content of oxygen in the water as the dissolved oxygen is able to escape due to it having a greater amount of kinetic energy and is leaving the surface of the water. So the water has a lower oxygen content to begin with due to its higher temperature and its lack of ability to effectively dissolve more oxygen gaseous molecules into it. We then sealed with a bung to stop any more fresh air really getting towards that nail, and you can see that it has had a marked effect on the rate of rusting. So higher temperatures decreasing the concentration of dissolved gases in the water, including oxygen, seems to have had a decent effect in reducing the rate of rusting. Okay, so experiment 4, that nail looks as fresh as the day we placed it into this boiling tube. So the drying agent below the nail, that anhydrous calcium chloride, has removed one of the key necessary substances for rusting to occur. It's continuously been removing moisture, water, from the air around the nail, so it's not in contact with water, only oxygen, and that is not sufficient for rusting to occur. So for rusting to occur, we need the iron nail to be in contact with both oxygen and water. This experiment has removed the water, and so no rusting has occurred. In experiment 5, we coated the entire nail in a thick layer of paraffin oil, a oily lubricating layer, and you can see there is a tiny amount of rusting on the extremities of the iron nail in areas where there was a poor covering, but the majority of the nail has not rusted. So what the oil is doing is it's providing a physical barrier. Not totally impermeable, but that physical barrier is literally preventing contact between the iron of the iron nail and the surrounding water and oxygen molecules. The water and oxygen molecules just can't directly get to the iron nail due to that physical barrier, and it's therefore preventing rusting occurring. The added advantage of oils and greases is they are lubricating, and therefore they decrease friction for moving parts inside engines, for example, but they are not perfect. If I were to wipe away that oil layer, or if it was to become removed in another way, then rusting would definitely occur because that physical protection, that physical barrier would have been removed. Let's now move on to look at what our metals were doing in these experiments. In experiment 6, we wrapped a piece of magnesium metal around our iron nail. And it looks to be the case that most of the rusting has been prevented, except this end here. So how or why has the magnesium metal been protecting the iron nail? Well, it's all because magnesium is a more reactive metal than iron, and it's acting as a sacrificial barrier. The more reactive magnesium metal is reacting preferentially with oxygen atoms instead of the iron, and therefore protecting the iron from rusting. In fact, it's acting as what we say is a sacrificial anode. When magnesium atoms are oxidized, they lose electrons to form magnesium 2+ ions. Those electrons will be transferred to any Fe2+ ions that form as part of the rusting process, turn them back into Fe ion atoms. They are reducing ions into iron atoms. And that's going to halt the rusting process entirely. So that magnesium metal is actively protecting all the surrounding iron atoms and preventing them from rusting because it's the more reactive metal. There is a little bit of rusting going on, and that's probably down to the fact that magnesium is quite a lot more reactive than iron, and maybe the magnesium at the very end here has been exhausted, has done its job, has all formed magnesium oxide, and there's no more magnesium in close proximity to that iron to keep protecting it, and a little bit of rusting has been allowed to occur. But magnesium's done a pretty good job of protecting the iron. And in fact, if we chose a metal which was a little bit less reactive than magnesium, but still more reactive than iron, it might have a more prolonged protective sacrificial barrier effect, and might be more suitable than magnesium for protecting iron from rusting. Experiment 7, we used zinc rather than magnesium. And again, it looks to be the case that the zinc has done a good job of protecting the iron now, only a bit of rusting at one end. And again, this zinc is more reactive than the iron and is acting as a sacrificial barrier, preferentially reacting with the oxygen instead of the iron and preventing rusting because it is the more reactive metal. It's also acting as a sacrificial anode, protecting the iron atoms surrounding it, because when zinc is oxidized, it loses 2 electrons to form zinc 2+ ions. Those electrons are supplied to any iron 2+ ions formed during the rusting process, converting them to iron atoms, helping to slow the progress of any rusting which could take place. So this piece of zinc is protecting the iron atoms all around it, and until it's been completely exhausted, it will continue to do so. And in fact, zinc might be a better metal to use than magnesium because it's slightly lower reactivity than magnesium, might give it a more prolonged sacrificial protection compared to the magnesium. So zinc is an ideal candidate as a sacrificial barrier. And finally, experiment 8, where we used copper metal wrapped around the iron nail. And oh dear. If our objective was to reduce the rate of rusting, the extent of rusting, then this experiment has genuinely been an epic fail. And it stands to reason that using copper rather than zinc and magnesium was a very bad idea. Copper is less reactive than iron, and therefore in this particular case, the iron itself is acting as a sacrificial barrier for the copper. The iron is preferentially oxidizing, is rusting faster to try and protect the copper surrounding it from oxidation. And so it's having a counterproductive effect, and actually by wrapping copper around our iron now, we've actually made things worse and made the rusting even more prevalent. So that may have been the wrong choice. So there you go, ladies and gents, that concludes our rusting experiment medley. I really hope you found it useful in understanding what substances are required in contact with iron for rusting to occur, and the methods we use to try and prevent rusting from occurring in the first place. As always, thank you so much for listening, and if you found this video useful, do please think about giving it a like. You could always subscribe to the channel. You could even ring the bell, here comes my imaginary bell, to keep notified of our latest content. I do put up videos on a weekly basis, and the more support, the better, as I try and spread the learning of chemistry as widely as possible. Thanks again for listening. Take care. Bye now.